Okay, so talked about rational expressions. We simplified some, we added, subtracted, multiplied, and divided some rational expressions. Remember, a rational expression typically consists of a polynomial on the top and a polynomial on the bottom, right, of a fraction. And so that would be our rational expression. Now we're going to talk about the functions themselves, and we're going to take one rational function, and we're really going to just tear it apart. By that, I mean, we're going to look at it in every angle we pretty much can. Okay, so rational functions, just to recap a little bit and give like a little bit more of a standard definition. It is a function of the form f of x is equal to p over x over q over x, where we're calling p of x and q of x polynomial functions. Okay, and so that's a rational function. Okay, basically what we talked about earlier, a rational expression, except in function form. Okay, so one thing to keep in mind whenever you're discussing rational functions are the domains and the range. Of course, the domain is going to be all the numbers, all real numbers, or just all numbers, so say all numbers. Where the denominator is not equal to 0. Okay, so that's the only thing we're watching out for. Anything that makes that denominator equal 0, we will exclude it from our domain. Otherwise, we're pretty much good. As far as the range, it's all numbers, all values, except wherever the horizontal asymptote is located. Okay, generally. Okay, that's generally going to be the range. And so we'll look at an example of all that soon. Okay, let's go ahead and go to our first and only real example here. So here's our function that we're gonna deal with. F of x equals x squared minus 9 over x squared plus 7x plus 12. And the first question I want to answer is the domain. What is the domain? Okay, remember the domain consists of all the numbers that you can imagine, the implied domain that is, and we're looking at all the real numbers here, except for anything that causes that denominator to equal 0. So let's identify what values would cause the denominator to equal 0. So we don't want the denominator to equal 0. Okay, so let's factor this. Okay, I'm going to look at x squared first. So we need an x and an x here. Looking at a 12 right here. So I need numbers that multiply together that equal 12. I have a few ideas in my head. I'm going to try maybe 2 and 6 first. 2x, 6x. If I added those together, I get 8x, which is not 7x. So I know 2 and 6 are not correct. That's wrong. So let me try maybe 3 and 4. There's my 3x, 4x, add them together, I get 7x. Okay, so 3 and 4 are correct, right? So I'm gonna go with those two. So x plus 3, x plus 4 equals 0. Set these individually equal to 0 to solve them using the zero product property. Subtract 3 from both sides. Let me not box it in. Subtract 4 from both sides. Okay, so those are two values that if I plug them into this equation here, or this expression here, I get 0. So I have to take those out of my domain. -3 and -4. Now, be careful, don't do this, right? -4 goes to the left of -3. So make sure you put them in order. These are holes in the domain. So all numbers smaller than -4, bigger than -3, and all the numbers in between. So all the decimals, -3.5, -3.9, right? All those are fine as well. So that takes my domain and breaks it into 3 sections. The first one, -infinity to -4. The second one is -4 to -3. Third one, -3 to infinity. And don't forget the u's in between to represent the union. Okay, so that's my domain. -infinity to -4, -4 to -3, and -3 to infinity. Since I factored the denominator here, I'm going to go ahead and write that down up here. We'll go back to that in a second, actually. Matter of fact, let's factor the top as well. X squared minus 9 is difference of squares. That's easy to factor, so I'll hurry up and do that as well. Okay, and so setting that denominator equal to 0 gave me the holes in the domain. Now let's talk about holes in the graph. Okay, so there's a difference, right? There's a difference. A hole in a domain means you're looking at just the x-axis, right? The number line, you're looking for values that you cannot plug in. A hole in the graph is the point that comes from, well, you'll see, an undefined point. So let's say we have our function, which we just factored as x plus 3, x minus 3, over x plus 3, x plus 4. Now you probably notice that you can scratch out that x plus 3. Okay, so the result is not the function, right? We didn't just simplify the function, but we have another expression here that is basically the same function with the exception where x does not equal -3. Okay, so that's the exception. These two functions are the same except whenever x is -3, because if I plug in -3 into the function, I get 0 over 0, right? Because plugging in -3 right here plus 3 would give me 0 on the top. Plugging in -3 right here would give me 0 on the bottom. So I would get 0 over 0, which is indeterminate. We don't actually know what that is. It's not 1, right? I know people think it's 1 sometimes because anything divided by itself usually equals 1. But it also, you also know that 0 divided by anything is also 0. So it's 0 or 1. No. It's indeterminate. We can't tell anything from that, which is why we have to simplify it. Okay, so back to the graph. We're going to work with this one's graph because that one is something that we can make sense out of. Okay. If I plug in -3, I get 0 over 0 for here, which is where the hole in the graph is going to be located. So to figure that out, let me plug in -3 into the simplified version. Okay, we know that something's going on at -3. We get -6 over 1, so -6. So at -3, -6, there's a hole in the graph. Okay. Yeah, there's a hole in the graph. And again, it comes from whenever you cancel out something over something else. That's definitely part of the original function. But if you plug in -3, you'd end up having 0 in the denominator. So you have to take that point out. So it's a hole in the graph. Okay, we'll have a visual of that. Actually, we can do that now. So here's the function that we're talking about. Okay, and we just discovered that there is a hole in the graph whenever x is -3. Let me zoom in a little bit. There's -3. Scroll down. Yep, there it is, right? It says undefined, and you can literally see there's an open circle there. It's a hole in the graph. Okay. Now, this thing is a complicated function to work with if you're trying to work it out by hand. So this is the simplified function. If you want to look at that, again, the graph is the same, except if I zoom in again on -3, it's defined, -3, -6. So that's what I did. We found this point because we knew that's where the hole in the graph would be located. Okay. Next part. Okay, so we simplified this. We found x plus 3, x minus 3, x plus 3, x plus 4. Okay, these equal I'm gonna put equal here, but we know they're not actually equal. Let me just put an arrowhead. How about that? Okay. So a vertical asymptote will be where this one, right? Once you simplify it, where that equals 0. So it's actually at x equals -4. That equation represents the vertical asymptote. Okay, so I want to recap really quick. If you have, so notice we had two holes in the domain, right? -4 and -3. These were bad x values we could not plug in. This one resulted in a hole in the graph. This one resulted in a vertical asymptote. Okay, so they're going to account for some, you have to account for them some kind of way. All the holes in the domain you have to account for. They're going to be one or the other. Okay. What does that look like? So here's the graph. Here's the vertical asymptote we just found. You actually can see it, right? It's this vertical boundary that the graph comes up close to, but doesn't actually touch. Okay. You can also see there's a horizontal asymptote we'll talk about in a second. I'm going to talk about that now, actually. Okay, so the horizontal asymptote, how do we identify that? Okay, well, without knowing calculus yet, you can't really work this out by using calculus methods. Okay, so there's a calculus reason for it, but you could just remember these three rules, and they're not overly complicated rules. Okay, and remember, since the two graphs are the same, whether you deal with the original function or if you deal with the simplified function, right? The graphs are both the same, so it doesn't matter which one you use. Go with the easier one. So x minus 3, x plus 4. Doesn't matter, but we're going to use that one. All right, so vertical asymptotes, horizontal asymptotes, remember these three rules. You look at the degree or the highest exponent of the top. If the top has the largest exponent, on the variable, then there's no horizontal asymptote. I do want to give you a visual of that. Okay, so the top has the largest exponent. Okay, so let me just make up one really quick. We'll close these out. Let's say y equals x squared minus 9 over x plus 5. Okay, horizontal asymptote, not there. Right, no matter what, if I just raise this exponent, and it just gets, you don't see a horizontal asymptote anywhere. Okay, they have to be the same, or this one has something on the bottom, but we'll talk about that in a second. Okay. All right, anyway. Okay, so the top has the largest exponent, then none. If the, let's see, if the bottom has the largest exponent, then the horizontal asymptote is y equals 0. Y equals 0. So if we had, let's say, 2x to the 5th on the bottom there, that would be y equals 0 for the horizontal asymptote. So what does that look like? Let's say, okay, well, this is one right here. And let's say we have y equals 0. You can actually see it there, right? You can see this line. You zoom in, you can still see, right? That green line stays above that purple line. It's the horizontal asymptote at y equals 0. Now, for our problem here, the degree of the top or the highest exponent is 1. The degree of the bottom or the highest exponent of the bottom is 1. So it's the same. So that's the case we need to account for. If the top and bottom have the same highest exponent or largest exponent, then the horizontal asymptote is y equals the leading coefficient of the top. That's the number in front of x, with the x with the largest exponent, or the leading over the leading coefficient of the bottom. It's harder to write that out than it is to actually work it out. Okay, and so leading coefficient of the top, leading coefficient of the bottom. If you look right here, the number in front of x is an understood 1. The number in front of x is an understood 1. And so the horizontal asymptote is y equals 1 over 1, or just 1. Okay, so that rules, right? Top has the largest exponent, you don't have a horizontal asymptote. Bottom has the largest exponent, your horizontal asymptote is y equals 0. If they're the same, then it's this. You just take the numbers in the front. Okay, what does that look like? Let's get rid of these. And here's our function. There's our vertical asymptote. Here's our horizontal asymptote, right? Y equals 1. You can see it there. You can zoom out, you still see it. Okay, so notice the asymptotes kind of serve as a boundary. It really does help you to graph this thing if you want to graph it. Okay, let's see what we got next. The roots, right, or the zeros. Okay, remember, you can work with the original. You can work with the simplified version. I always recommend that you work with the simplified version because it's easier to work with. Just pay attention to any holes in the graph, right? But you already know that -3, -6 is a hole in the graph. Okay, so we're not going to allow that to be one of my roots. Okay. All right, so anyway, so let's solve x minus 3 over x plus 4 equals 0. If I multiply both sides by x plus 4, that'll get rid of the fraction. It's kind of an unnecessary step because when you multiply both sides by x plus 4, sure, it cancels out on the left side, leaving you with x minus 3, but 0 times x plus 4 is just 0. So I could have just set the numerator equal to 0, which would have also made sense. Add 3 to both sides, and I get 3. All right, so I have a root whenever x is 3. Okay, and it works for either one you plug into, whether it's the function or the simplified function. Okay, and we can see that on the graph, right? Whenever x is 3, y is 0. That also makes this an x-intercept. Not even gonna have to work that out. We already know it's 3, 0. If you find the root, you found an x value that gives you a y value of 0, which is an intercept, an x-intercept. Okay, the y-intercept, however, you find by making x 0. So I'll plug in 0 for x. That's going to give me -3 over 4. -3 over 4, right? Or -0.75. Okay, and again, we can see that on the graph. -0.75. Okay. Now that I know where the asymptotes are and I know where the intercepts are, I can sketch the graph. Remember, we talked about this last week. You do want to have a base idea of what each looks like. So here's the generic rational function, okay? And we know that that looks like this, right? So you want to memorize that, because just knowing that will help you to sketch the graph. Okay, so let's draw, maybe put a bigger graph here. Okay, we have 1, 2, 3, 4. At -4, we have a vertical asymptote. When y is 1, we have a horizontal asymptote. Okay, and so you can look at that as the the new cross section here as the new X and Y axis if you're looking at the graph. So it's probably gonna do something like this, or maybe something like this. Okay, but you can look at that as the new axes. All right, and then we know where the intercepts are, right? We know that the x-intercept is whenever x is 3, and the y-intercept is at negative 0.75, so that would be right there. Okay, and so knowing what the graph kind of looks like, it seems like it's doing this. And it's going to curve downward. So to the left, I'm sorry, to the right of the vertical asymptote, we know it's going to be below that horizontal asymptote. Now we need to figure out, well, what is it doing over here on the left side? So here you should just pick a point. This is what, -5. Plug in -5. That'll give you the y value for this point. A point that's to the left of the vertical asymptote. So that's going to be -8 over -1, +8. So -5, +8 is part of the graph here. That's going to be up here somewhere. Okay, so again, knowing that the shape is going to be either like this, or like that on the bottom, and like this, or like this, and have a point up here, I know that the graph's going to do that up here. Okay. Oh, and we also know, I guess I didn't need to find that point because we also know that there's, wait, yeah, I did. At -3, -6, kind of guesstimating here, there's a hole in the graph, right? We know that as well. Okay, so that's our rough sketch of the graph. Again, we can compare it to the graph here. It's the same graph, right? We see it. Of course, this is a lot nicer than my hand-drawn version, but we see it. Okay, so that's the sketch of the graph. Let's use that now to discuss the, I think it's, yeah, the range. Okay, so the range. So remember, the range would be the y values. Notice how the range is like a number line this way, broken up into two sections. -∞ to 1, and then from 1 to +∞. Those are the two sections, right? First one here, second one there. So the range would be -∞ to +1, and 1 to +∞. Okay, and then finally, yeah, last thing, let's find the inverse. Okay, now again, remember, let's go back to this. The original function and the simplified function, they're practically the same thing. You can work with the simplified function as long as you make sure you acknowledge that there's a hole in the graph. Okay, so let's do that. Let's work with the simplified one. So y equals x minus 3 over x plus 4. I'm going to write right here, so don't forget that -3, -6 is a hole in the graph. Okay. So for the inverse, all the x's and the y's are going to switch. So for the inverse, -6, -3 will be a hole in the graph. Okay, so x equals y minus 3 over y plus 4, right? We invert our x's and y's. Let's multiply both sides times y plus 4 to get the fraction away. Distribute the x. Cancels there to leave you with y minus 3. I'm going to subtract y from both sides to cancel this one out. That'll leave me with x, y minus y. I'm also going to subtract 4x from both sides to get rid of this one, trying to get the y's all on the left side. All right, so again, I subtracted y and subtracted 4x, so they basically switch places. Factor out a y. Divide both sides by x minus 1. Okay, so there you go. That would be my inverse. Except, of course, whenever -6, -3. Except whenever x is -6, -3. All right. Let's see what that graph looks like. And then we'll be done. Okay, so maybe it's a little harder to see the symmetry there. Let me hide some of this stuff to make it a little bit easier. Okay, you kind of can see it actually now, right? If you imagine that there's this line going across the origin, through the origin. Well, doesn't look that great, but I don't know, you kind of can see it. Maybe. Anyway. All right. Let's see. It's because that's supposed to be a 3. That looks better. Okay, now it looks better. All right, so you see we have a little bit of separation here and here. These two are mirror images of each other. And if you back out, this one is the mirror image of this one here. Okay, only stipulation we need to watch for is -3, -6 is a hole in the graph here. So whenever we write out our function, we would want to say that -3, -6, -3 is not defined. It's also a hole in the graph. All right, that's that.